Okay, this part of the stuff's my fault in the beginning, the early stages. Okay, this is why you all came here. Okay, I don't know if you want to go around, we can introduce people, or if anybody wants to stand up real quick and say who you are. Starting here. Cool. He's the other cohort.
I'm Bill Lucas from Mechanicsville, Virginia.
Glenn Hogue, Glenn's Garage.
Townsend, Lakeville, Florida.
David Andrewsick, author of MegaSquirt.
Phil Tobin from Charlotte, North Carolina.
Jeremy Porter from Raleigh, North Carolina.
Leon Stevens, Watsonville, Georgia.
Tim Fleming, Murrayville, Georgia.
Andy Whittle from St. Louis, Missouri. Where? St. Louis.
Philip Ringwood, Dextershire from England.
First time in the States?
Third
time, okay.
Jim Anna, Barry. William Madison from Greenville.
Okay.
Eddie Howard from Montgomery, Alabama.
Johnny Spears, Montgomery, Alabama.
Chase Hawkins from Spartanburg, South Carolina.
Jennifer Moyer here with my husband. How are you?
Josh Hawkins from Spartanburg, South Carolina.
Mike Gianfrido from Connecticut. Chris Ladden from Connecticut.
Dan Becker from Perry, Georgia.
Kyle Moss, St. South Carolina.
Bunch of guys.
Scott Black.
Michael Lindsay from Lawrenceville. Richard Knight, Tucson, Arizona.
We're missing people. Where are you?
Lee Williams, Bethlehem, Georgia. Peter Florence, Virginia Beach, Virginia.
Who's not here? Yeah, where's James and Ken? They're next door. Okay. What are they doing? Fixing software, right? Good. They're putting a new mode in there. We're going to get it all working. I'm going to hand them some hardware to fix. All right. What I'm going to go here is a little bit of training. Everybody has different backgrounds. We want to do is these MegaSquirt meetings start going. We get more of these. Is touch a little bit on theory and also touch on hardware and ask a lot of people questions. And what I want to start with here is get some general feedback on MegaSquirt. What do you all like about it so far? From the audience, you all. It works sometimes, yeah. How often does it work? Yes. Who has not let the smoke out? Okay. Only one person. Great. Okay. What else? It's cheap. Yeah. Versatile. Open source, meaning people can mess with it, and they're in the back room right now coming up with a new function that we're going to have in the next 15 minutes. Never obsolete. All right, what's frustrating you about it? Now this is an open thing. Okay, what was that? Noise. Anything else? Okay. What else? That's it, noise. Okay. We're going to have a slide, not this one, but in a little while, going over noise and some of the things you can do on different installs. Because the thing with noise is it's different for every car. Whenever you can put it on one car, it'll work fine. You pick it and put it on another car. Everything's identical, and it won't work. And you'll like, what's different? And there is something different. You get to figure out what it is. All right, and we'll just give you ideas on how to do it. All right. So we're going to start with theory. Now, I have to apologize in the beginning here because over the last week I was working on these slides, and I didn't get them finished, anywhere near finished. So we're going to get hot and heavy and stuff in the beginning, and then it's going to fall off at the end. And then we'll have MegaTunics come on. What we'll do is just be the teaser for the next MegaSquirt meet. I'll get some more slides done, and we can start delving down even deeper. Okay? Questions so far? All right. Yeah. What's the noise? Oh, you haven't heard about the MegaSquirt noise. Oh. Anybody want to explain the noise? What? Oh, tell them. Let them know what they're in for.
You know, when you get noise on your radio, it doesn't sound quite right. Well, when you get electric electrical noise is when it's something that should be a steady signal gets a bunch of, yeah, it gets kind of fuzzy. And noise in a fuel injection system, instead of making the speakers not sound right, can make the injector pulse width or the ignition timing not come out right.
Good. Any other questions? I mean, that's a good answer, right? That noise is bad. Okay. Yeah.
One thing that's not frustrating to me, but something in the comment that I've got from a lot of users is, and it's not a shortfall, but it is something that it's actually a strength and a weakness, is the lack of centralized authority. It's like Linux, it's kind of spread out everywhere, which is really powerful, but people who just get involved in it seem to not know where to go.
Okay.
It gets, depending on what they're trying to do.
Get started.
Yeah, there's a lot of confusion between.
Okay.
Getting started too.
But that may be good because that allows a lot of innovation, and there's not any Bill Gates component to this, which is really cool.
Right. I mean, it is. It's a balance. A part of it is a lot of people are helping with the project. Okay, putting their spare time into this, and they're doing it for fun. And this is not a polished commercial product. As time goes on, it gets better, and we try to regroup. And it's evolutionary process. So. But it's designed up front that you have to work for this a little bit. It's cheap, and you have to kind of work. You have to understand this stuff, because if you don't understand what you're doing with the install, it may not be successful. Noise might get to you, and if you don't know how to combat it yourself, you may not get this one working. And it turns out most aftermarket units can have noise in it. You may put a box A, it works, put box B on, it doesn't work. Okay, you knock the side of the box B and it springs to life. Box C works sometimes. They really act this weird ways, and it's not so much in the electronics. Some of it could be in the electronics in the box, but a lot of it is the environment around it. And what we're trying to do is make people dig a little bit for the knowledge before they just take this thing on and just slap it on and throw a switch, because you're going to get frustrated. And we know we're hearing the feedback about being frustrated about finding stuff in the manual. We got to work on that to make it a little easier as well, and make it. We're looking at things to improve the organization of the manual. Content, it's always being revised. Because part of the problem is every day, Ken and James and Al they won't stop putting functions in, which are great, but then they have to be documented, and it has to kind of flow with everything else. So that's what's cool about this thing, and that's also at the same time what's kind of frustrating. So you will be frustrated at some point with MegaSquirt, okay? Just realize that, okay? All right. That's part of the fun. That's why everybody's here.
You ever mess with a hydrocarbon?
But it's a metal with holes in it, right? You know, how frustrating can you be? You can always just drill a hole out and not JB weld it in and drill a new hole, right? Who has not done that? Here, DB921 burns up, slap another one. Okay. All right, let's go on to the fundamentals real fast. We're going to make a cake with an engine control. Okay, it turns out air and fuel, you mix it together and you give it a spark and you get a nice explosion. Okay, this cake is octane. Okay, so we take a hydrocarbon. What is hydrocarbon? Gasoline. Different type, ethanol, whatever, something that burns. Diesel, wood, got hydrogen and carbon in it. It's important. That's why it's called hydrocarbon. It's not just someone coming with a cute name. There's the word hydro, which is hydrogen, and carbon, which is carbon. You mix it with air. That's the trick. How much air do you mix it with to make, and add a fire to make a nice explosion? Okay, now this is what you want. This is what you want. Now inside your car, not outside. All right. Okay. The most important thing, if you got the mix right, you get a cake out of it. Well, in our case, we get water and carbon dioxide. That's the whole gist of this. Our goal is to make water and carbon dioxide, plus make the explosion, make the piston. And heat, yeah, it's a result of the reaction. What was that? Heat's the useful part. The amount of water and carbon dioxide, this is a perfect boom. Okay. All the oxygen, all the hydrocarbon got consumed with oxygen in the air. Okay. There wasn't anything left there. There wasn't too much of this and too much of that. If you're making a cake and you put flour in it, you put sugar, I can fill the thing up with a lot of sugar and very little flour, and the cake's going to be horrible. And I can go the other way, and the cake may not be good either. But if I get a certain mix, it's always happy. So the whole goal is to get your hydrocarbon, these elements, to combine with oxygen to produce heat, the most useful heat, and the remnants, which come out of the exhaust pipe. Okay? You get the boom part, and you get all this junk, a whole bunch of stuff that comes out with it. All right, this is where the EPA spends their life. They want to minimize a lot of these things. Questions? Isn't this simple? Again, and I said just to drill down into it, you have a fuel and you have air, certain amount of hydrogen and carbon reacts with oxygen to get carbon dioxide and water, and you always get nitrogen out. All right, this is a perfect boom. Okay, imperfect boom means either I had too much air to gas, or I had too much fuel, hydrocarbon, to air. Okay, everybody knows what that means. What those are called rich and lean, right? What's better? What's better for this crowd in here? Rich, hey, rich, right? Rich pollutes more, though, right? But we don't care, right? We do care. We care in the film. We care about pollutants, okay? A, it's regulated emissions. Everything is boxed. They'll hunt you down and kill you for this. So do not pollute, okay? Okay. Just remember, if the mix is perfect, you get CO2 and water, okay, for a perfect mix. Imperfect mix, if you have air, too much air for the fuel, you get O2 left over. Why is that? It's a real simple answer. I mean, it's not a trick question. All the fuel's consumed, and you still have air is left over, right? So it's kind of comes off for a ride, right? That's a lean situation. So you're actually sucking in air. You sucked in more air than the fuel has consumed. And it turns out, when you're in the lean mode, you don't get a lot of other combinations of other chemicals coming out, or other particulates coming out. Now, on the rich side, you get a lot of extra junk out of it. Okay, it's rich because what happened? Not enough air. So you have the nitrogen combines with some of the stuff left over, and the hydrocarbon. You get all this junk out of it. All right. So everybody knows stoichiometric. You all heard stoichiometric? What is stoichiometric without reading the slides? Chemically perfect, meaning the result will be... Yeah, see, well, why do you know? Here, I'm going to give you this. This is good. That's awesome. You're absolutely right. That's all this is. And you can read this whole thing, and you could spend your life... Everybody has gone through chemistry classes, had to balance equations. Well, this is the balance of this equation. And they go through how all this is consumed with the oxygen, and the result, the arrow means you've gotten your spark, and this is the result coming out. Okay, you're just trying to balance atoms. Okay. We are going to talk a little bit about some of the terms used outside of what we're used to. We're used to hearing air-fuel ratio. What does air-fuel ratio mean? The ratio of air to fuel, right? Everybody knows the numbers, right? What is stoichiometric? 14.7, 14.5. What is 12.5 to 1? Is that rich or lean? So everybody in this class knows this. Every class. On the other side, lean, 20 to 1 is lean, right? That 14.7. What you can do is it's basically an air-fuel ratio. There's another term that is called lambda. And what you do is you take your air-fuel ratio actual, and you divide it by the air-fuel ratio stoic. And what happens is you get a value that 1 represents perfect combustion, stoichiometric point, 1.0. And if it's less than 1, the mix is rich. Okay? So if you have a number less than 1, like 0.9, 0.8, 0.8, you're rich. If you're greater than 1, it's lean. Okay? So you basically just do the thing. So the reason for doing this is that different fuels, the hydrocarbons, if you burn an E85, the stoichiometric point moves from 14.5 to, let's say, 9 to 1. Well, if you want to tell someone to be a little bit richer than for E85, you can't banty a number out 12.5 to 1, because that would be really lean, because the stoichiometric point moves. So, but if you use the word lambda, you tell them, well, be 0.95 lambda. It takes into account the change in stoichiometric point, value point. Okay? Is he clear? Is everybody confused? Yeah. Who's confused? That's right. That's right. Simple. Now it's time to get confused. Because engineers a lot of times I call them idiots. They like to rearrange stuff because they can. They came up with a thing called an equivalence ratio. What come in here? All an equivalence ratio is 1 over lambda. Why? I don't know why. They just do it. If you read in a lot of text, they will talk about this equivalence ratio. It's just 1 over lambda. It's the same thing. Okay? It's just what you're taking is the stoichiometric point, dividing it by what you're measuring for your air-fuel ratio. It's just the inverse of it. It's a little bit more intuitive because for this crowd, rich usually means more. It's bigger. We're all like the rich. So an equivalence ratio greater than 1, you get a rich number. If it's less than 1, you get a lean number. Okay? I love the lights here. It's cool. All right. This is a cool graph. Because down here in the bottom is equivalence ratio. And this little line right here that I stuck in is 1.0 equivalence ratio. Over here, are we rich or lean? On this side. Rich. And over here, we're lean. Okay, so the important thing we have here is when we're lean, we have O2. We get a lot of O2 out of it, right? We talked about that earlier. It didn't combine. And we also have other molecules on this side, but when we're rich, we get all this other stuff that pops up, and the amount of it goes up. Like CO is low on the lean side, but it goes up to a certain point and comes back down as equivalence ratio goes over. Isn't that cool? Aren't you excited? All right. Beers come later, maybe, so that'll get you a bit there. Okay. A few more subjects that we're going to touch on here, and then we're going to pass it on to the next people, is something people keep asking me, why do we use mass air and mass fuel instead of just air and fuel? You'll hear mass airflow sensors and the mass of fuel from your injectors. Why is it mass and why isn't it just the amount of fuel, the volume of it?
There's molecules.
Yeah. Right. That's it. So we're done. We're done. He's absolutely right. I have slides on here. We'll go through. We'll just burn through them real quick. But that's the whole thing. And what we have to do is we have to deal with mass and not with volume, especially with air, because we say, oh, well, I have a volume of air, but there's actually a certain mass to it. And that's what's important is the mass of the air and not so much the volume. The volume is important and the temperature is important, but you use that to compute the mass. Okay. Density is mass over volume. Things have molecules. Molecules basically have an intrinsic weight. This goes through a whole bunch of stuff. If we cram more molecules in something, its mass increases. There's a whole bunch of stuff. How many grams? A gram is this much larger than a carbon atom. It's exciting stuff. Okay. Atomic mass unit. Every one of these little thingamabobbers here has an atomic mass unit to it. Okay, is a definition for it. And so what you do if you have something that has a bunch of carbon, each one of those little carbon molecules will have this mass associated with it, and you add up all the masses. Okay? You don't have to worry about any of this. So that's why it's up here. Okay. Does air weigh anything? Because it has mass, right? All right. Ideal gas law. Has anybody heard of the ideal gas law? Well, you have. Of course. These people here can't answer. Okay. High school, so everybody knows about it, right? This is what MegaSquirt is all based on, ideal gas law, and all the EFI systems out there. They all use ideal gas law, okay? You have a volume, and you have a pressure, and you have a temperature, and the little n is what you're trying to find. You're trying to determine the number of molecules, I think of them as ball bearings, in a volume, okay? And I can press more in there of a pressure. I can change the volume, and the volume will make the little molecules spread apart. Okay, the most important thing is this law right here. This is MegaSquirt. This is MegaSquirt right here. All right, and it's ideal. Okay, this picture here is just showing the cylinder. We all know about it. We have an air intake tract. This valve opens up. Air comes in as this thing goes down. Why does the air come in when this goes down? You're increasing the volume of the compression chamber, and that in turn causes what? Drop in pressure, and you have this opening here, so it all gets sucked through here, right? That's all it is. Okay, the little thing about it, if you want to know how much air is in the cylinder, this is a cylinder, it could be a tin can. If I hand you a tin can with a certain pressure of air and I know the temperature in there, I could should be able to compute the mass of the air inside of there, right? I like to look at it as a jelly jar full of jelly beans, little molecules, and I can cram more in there. Each jelly bean has a weight. If I cram more in there, its overall thing weighs more. Any questions on this? Is this boring you all to death? Isn't it great? No, I mean, everybody understands this, because if you understand this, you know everything about MegaSquirt now. You know as much as the rest of us do, okay? This is all that's going on in computations. All right? Okay. One more part that I'm going to touch on here is something called volumetric efficiency, which is another question people ask. What is volumetric efficiency? We're going to go over it right here. Who has heard of the term volumetric efficiency? Who has not? In the back. The new people in the back. I don't know why you're in the back, but you're in the back. Why? Oh, you're new too? Okay, you've heard of volumetric efficiency. Who has not heard of it? Oh, well, we don't have to do any of this. Okay. What is it then?
How much of the cylinder actually gets filled up when it expands?
Yeah. Right. You have a cylinder, right? And it has a certain volume when the piston's down. Air can get in there. How much air actually gets in there, they call it an efficiency. It's really not an efficiency, but it's basically a ratio of the density of the air that got in there versus how much I could have actually got in there based on the pressure. Okay? I could have a pressure outside of the valve that is atmosphere. When it comes in, and maybe I only got one molecule in there. Okay, so how much air actually got inside the piston, outside the cylinder is less than what's outside of here. If the efficiency means if everything was all right, the density of the air out here in the intake manifold will equal all the density which is inside the cylinder. And if I know the density of the air in the cylinder, I can compute the number of molecules and go through it. But it's not the way. Sometimes, a lot of times it's less than that. Sometimes it's more. Yeah. Yeah, we're going to see a graph. Yeah, you're absolutely right. What drives the volumetric efficiency? Why, if I open a valve and air rushes in, why doesn't it equalize, and why doesn't all the air in the manifold equal all the air that's in the piston? Why aren't they the same, right?
Air can't move instantaneously.
Right. But
that's one thing.
Yeah, that's how much gets in there. Right. But that's one thing. But I will also counter at I can go 10,000 RPMs and I can get a volumetric efficiency of 100%. But at idle, my volumetric efficiency goes way down. And I'm measuring the pressure in the manifold. How come I had a long time for that valve to open and get in there? Why weren't they the same? Throttle, but we measure the pressure in the manifold. Okay, after the throttle plates, there's a pressure in the manifold. The whole gist of the speed density method is that the pressure in the manifold is pretty much equal to the pressure in the cylinder. If you didn't have that assumption, none of this stuff would work. You'd have to measure the pressure right in the cylinder. Okay, so you measure it in the manifold. The assumption is that pressure, whatever that absolute pressure is the same that's in the cylinder. Well, if it's the same that's in the cylinder, the volumetric efficiency should be 100%, right? Because it's the same pressure, and we went through the whole exercise. But it isn't. And why? It's like what Andy says. Because a lot of times, from your previous cycle, you have residual gas, excess gas from the last time coming through. That's displacing what the air could actually take in there, right? Port tuning has a no, because it can ram it in. That's exactly right. All the valve overlap, valve position, the timing, all that all drives this, okay? This chart came from Haywood, and it talks about what drives volumetric efficiency. This is really cool, because when you're done with this, you're going to say, hey, why can't I have one map from this engine and just use it and plop it down this other engine? Because you hear it all the time. Oh, I want maps. I want maps so I can get something close to my engine. When we're done with this, you can see it's lucky that any map works at all in an engine. You have to go and touch them up. Okay, you can get close with a map, but you're going to have to go in there and fondle the map in some certain way to get it going. All right? Yes. Forever and ever and ever. Okay. Think of tuning a VE as a good thing, not as a bad thing, right? All right. Lots of curves here. On the bottom here, mean piston speed is how fast the piston's going up and down. It's really, think of RPM. And over here is volumetric efficiency, and that's 100%. Okay? What we have here is the A curve, this one right across here. It's pretty flat. This is steady state, non-speed dependent effects, which drop VE below 100%. In other words, if you didn't have any effect except air was rushing in there past the valve, it didn't matter how fast the speed went across, you would have the same amount of air in there. It could be 100% if everything was perfect. Maybe you have a little bit of a drag because the valves don't pass the air enough, but it's constant. Okay? That's the top line up here. That's number one. When the air comes into the manifold, it gets hot, right? How long is the air in the manifold? Depends on how fast the engine's running, right? If it's a real slow running engine, the air has longer residence time to sit in there and get heat from the manifold before it gets sucked into the cylinder. What happens when air increases in temperature? Right? What would that do to VE? It's actually in the chart. Makes it drop down. So basically, A goes down to B. Okay? And it's lower. This sat in there a longer time, right? Slower. Air was in there slower, and then it got sucked in. Faster air just whooshes in. Doesn't have enough time to get heated up. Okay? What would drive this? Your intake design, right? If I had a big intake, a little intake, your runners for your intake. Is everybody's intake the same? Do people have little snorkel tubes coming in and sucking, all these things are different. Yeah. All right, so A went to B. Okay, everybody understands why, right? Air got hot. Slower air got hotter. Okay. Friction losses drop B, this curve, to C. Okay, it's basically the piston losses in the piston, the heat generated by that, and it's basically proportional to the square of the engine speed. So now all of a sudden VE is now dropped from this down to here. So we're screwing up our VE already because of that. All right? All right. What happens when the air speeds up in the engine? What happens? You talked about it earlier. It's harder for it to get in, right, because it can get choked by the throttle plates or by your valves, the flow. Higher speed, it's harder to get the air in there. That drops C to D. So now we've really screwed volumetric efficiency at higher speeds. Everybody see that? You see why? It's faster speed, I got to get across the valve. There's not enough time to get it across there, it drops. Okay, now we were talking about induction ram effects. Now we can take D and we can make it go up to E here. An induction ram effect. Does everybody know what an induction ram effect is, right? Basically, you tune your intake port and you get pulsations, and if you're in phase, it can actually help you. So you can get a little boost here at higher. So D goes up to E. Okay. You can start screwing around with your valve timing, and you can actually help. You can screw up your volumetric efficiency at lower RPMs, but you can actually help it at higher RPMs. And so curve C can go up to D and go up to F. Where's F? Here's F. Okay, so now we're starting to get a volumetric efficiency. We went up a little bit here, we went a bit down here, but we actually can screw up the valves and move the curve even more so. Now, how many people have different cams in their car? Everybody in this room has a different cam. Again, if I have one map, if I have a different cam, it doesn't apply anymore, right? All right, that's what this is showing here. Okay, you can do some more intake and exhaust tuning, and you get curve. Where's G? There's G right there, the final curve. Okay, that's your VE curve. The whole gist of all this is that you ask yourself the question, with all these independent things going on, how can I have one map that I can go plop to another engine, and it's 100% tuned ready for that thing? Everybody agrees you can't. There's too many things going on that can mess you up. And a lot of it is you guys screwing with your intakes and your cams and everything else. It messes up VE all over the place. So really the takeaway here is that you can start with a map, you'll get your engine running, but you got to tune it. And the whole concept of I want a generic map that will run with my engine, you're going to have to touch it anyway because of all this. Okay? This came from Haywood, which is, we have the book in here. It's the Bible of automotive engineering. So that's what I have right here. Any questions? I know you'd have a question. What do you think? We'd have to make you go up here, right? Because we can have VE over 100%. Okay. So what would screw up the VE? I mean, just learning from here. Part of the thing is, yeah, you get more pressure in there, but going through a turbo, the air might get hotter, right? Yeah, charge heating. So all these things are going against you. You get more, but then you get sucked away over here. It may be speed dependent, right? And turbo's more efficient at certain speeds. The VE is also changed by exhaust back pressure. And one thing people know, if you change your wastegate position, you got a whole new VE. You know, because your resistance of letting the gas get out of the exhaust is different. So you can just by tuning your turbo, it all feeds upon itself.
You see somebody with VE tables in 175 or 190 or something like that.
I wouldn't expect it, but someone in here probably has one. Who has one? Yeah, of course Andy does.
Okay, now, what would you use to
No,
determine?
it's efficiency. There's a certain limit to how much you can cram in here mechanically. Okay, with MegaSquirt, we have, it's a little bit of a wrinkle. All the stuff we have here is air. I have not talked fuel at all. There's no talk of fuel. This is nothing but air, how much air is getting in here. Okay, we use AFR to determine an air-fuel mix afterwards. Okay, so we have a value rec fuel which scales everything, which can offset your VE table up and down. You can make your rec fuel high and make your VE table across the board low, or vice versa. You can skew your data. So these absolute numbers are hard because if you got rec fuel wrong, your whole VE table absolute number is wrong. Now, relative numbers, they're fine, but as an absolute number, I can set my VE to be 200% by mucking my rec
I'm
fuel.
assuming that
You multiply the two
manifold
together, you get the
pressure
result. Yeah.
compared to cylinder, not pressure. Manifold is VE is a ratio between manifold and cylinder, correct? Right. So
Pressure.
It's not ambient air.
It's the ratio of the
If you're
density.
making
Yes.
40 pounds of boost and it was 100% efficient.
It's not ambient air. We measure it in a manifold.
Set up at 100.
Okay,
I think that's the question they're getting at. They're thinking if you're making positive pressure,
It'd be 100, but your map would
in order for it
read
to be
over.
proper,
And he's
it have to be in the
Okay.
over 100 numbers.
right. The fueling is, and I wish I'd written it out, but I didn't have time. The fueling equation is manifold pressure, absolute pressure, times VE. Those are the two drivers, and that's your exact point back there. Two numbers. Manifold pressure is the pressure in the manifold. And if I have a turbo, that'll boost up. You know, we got the Map Daddy board that'll measure 5,000 psi, and because there are people out there blowing average, whatever the number is, and you need it. It's people are running. It's not enough, but that is multiplied by VE. That's the important part because the VE says, hey, I'm measuring the manifold pressure, and I'm using that as a reference to what's going on in my cylinder. Okay, but my cylinder is not 100% efficient. It didn't pull in all that air, so I'm doing a correction on my map times VE, which is the spilling efficiency. Okay, so yeah, VE can be less than 100%, but I can have a bigger manifold pressure. Okay, you multiply the two numbers together, that's going to tell you what's inside your cylinder.
In my mind, what I'm trying to say is,
Understand?
if
Do
you
you understand?
multiply with the request,
Right, okay.
the fuel part of it, just be aware that the VE table is also affecting it, and vice versa. And then, at final instance, what am I going to use to say, okay, I got my tables correct? Well,
Really, it's up, and I hate saying it, passing the buck back to you, but it's up to you to what you're after performance-wise. Okay, and also, you may want 14.7 to show up on your narrow band and have 14.7 everywhere. Now, I can set a ref fuel to a constant, and I can trust all my VE numbers till I have this thing reading 14.7. If that's where you want to be, you're happy. And it doesn't matter if the VE number is skewed a little bit, you're happy. It's the absolute VE number. The way MegaSquirt's set up, it's a little hard to determine because the problem we're doing, these are airflow measurements. We're assuming airflow measurements. If we had a mass airflow system, it'd be different. We have that in the code. But if you use the speed density, which most people do, you have to assume what it is. Okay? Rec fuel can screw you up as well, and you're making the combustion, and you're measuring in the exhaust wideband or narrow band, and there can be errors all over the place. There can be extra oxygen coming and screwing up your wideband reading. So we're looking at a result to try to backtrack what a table is. And there are errors along the way. And rec fuel doesn't help things. Okay? No, repeat. It can be real VE, but probably nobody in this room has it absolute. But it represents VE. Yeah, right. Well, again, you show them this and say, well, what is your standard? Maps are maps. Every map's different. So what's the standard? The only real way to do it is measure the absolute error that came in with a mass airflow sensor, do it by the volume, and go that way. Okay. And it doesn't matter, so don't get hung up by the numbers, because the error can be in VE. The error can be in your fuel pressure flow, or not your fuel pressure or your flow of your injectors, because if that's biased off and you read your AFR, because remember, we're using the result of an air-fuel combustion boom exhaust gas to come back and fix this. There's error sources along the way. If anything has an error, it'll go back into here. But it doesn't matter. So don't worry about the numbers. All right? Oh, you want to talk about that? Yeah, I didn't talk about fuel, but we were talking earlier about how do you know what AFR number to tune to your engine to. And there's a lot of people have different methods. This is one method I've heard of and I've heard used very often, is to hold your engine at a fixed RPM, change your air-fuel ratios, AFR tables. You could use VE to do the same thing, and map the torque. Torque is going to kind of go up till you get your maximum AFR, whatever that number is. Maybe it's 13.5 to 1. Maybe it's 14. Maybe it's because the wideband's wrong and you got air oxygen. Maybe it's 12 to 1. But you keep stepping it up until you find the maximum, and it'll start dropping down again. The maximum is your maximum. Whatever that number is, it might be 13.5 to 1. It might be 14 to 1. It might be some other number. Just grab that number and say, that's my maximum for my, and tune to that number. Not that I read in the magazine 12.5 to 1 is the best everywhere. You can do that, and it'll work, and you'll be fine. But if you're trying to get that maximum bit, and you have a dyno that'll lock down your RPM, just do a simple sweep, and you'll see a curve go up and go back down. Try to find the peak. That's what we're at, right? We're trying to find that peak. That's all you have to do.
He'll take a sweep, with what we feel like is pretty good AFR, then he'll bump it by a few, he'll have you bump that row by a few points, up and then down, and overlay those curves over top.
Yeah.
Now we get a feel for what AFR.
Yeah. That's it. That's it. You can do 3 shots, or you can do a fit through it. You can do it's a parabola fit. You can do a parabola fit through 3 shots, or you can do a lot of shots. You can just keep bumping it up and write the numbers down and go to Excel and plot it out, and you'll see a point where you have the maximum point. That's your happy spot based on your measurement equipment and based on all the errors that can come down. So if it's 11.5 to 1, just use that number because you've proven it's the best from a dyno run. Okay. It's like what you were saying earlier. Don't get worried about the absolute number. Find the best number.
Different piston speeds that you may need a different AFR and different RPM.
What Haywood says in his book is that it's very much independent. If you can find that point in a couple places, you're going to see it's going to be about the same for the whole engine operating range. There may be some bumps here and there, but their recommendation, because it's too hard to go to every little place and bump it and curve and curve and curve. Do it at certain places and see how much variability is in there. But they're saying it's pretty constant across the whole operating range. So once you have that number, you've flushed out all your test equipment and you got this number that's happy with you. Use that number. Okay? That's simple to do. We can do it right out here. Use that as your target number. There's nothing wrong with that. Absolute numbers, don't get hung up. You find your happy number, your happy place. Yeah, we all have happy places. All right, so who's next?